During the space race, the world's attention pointed upward. Rockets climbed, satellites crossed the sky, and two superpowers competed beyond the atmosphere. But another Cold War project moved in the opposite direction. On a remote peninsula above the Arctic Circle, Soviet engineers began drilling into the continental crust. Their machine would eventually reach 12,262 meters below the surface. That is deeper vertically than the Mariana Trench is below sea level. Yet the borehole reached only a fraction of the way through the crust beneath that part of Russia. It never approached the mantle, much less Earth's center. What stopped it was not a supernatural discovery or a sudden order to seal an abyss. It was a combination of geology, engineering failure, extreme heat, and disappearing money. What the scientists actually found was stranger and more valuable than the legends that followed. The Kola Superdeep Borehole, known as SG-3, was part of a Soviet program created to study Earth's deep continental crust directly. The project developed during the same era as lunar exploration, and Soviet researchers sometimes compared its ambition with spaceflight. But it was not simply a secret attempt to defeat America underground. Its stated objectives were geological: recover deep cores, measure physical conditions, explain seismic boundaries, and investigate mineral formation. For its first 14 years, the project remained largely hidden from scientists outside the Soviet Union. That changed after SG-3 passed 12 kilometers. At the 1984 International Geological Congress in Moscow, Soviet researchers presented results in English, displayed cores, and organized visits to the installation. The borehole became both a research platform and a public demonstration of Soviet engineering. In 1968, specialists selected a site roughly 10 kilometers west of Zapolyani on the Kola Peninsula. The area lies on the ancient Baltic Shield, where very old crystalline rocks occur near the surface. It was also part of the Peshchenga ore district, so drilling could test ideas about deep copper and nickel mineralization while crossing some of the oldest accessible continental crust. Drilling began on May 24, 1970. The first rig was an Ural-Mash 4E, equipment originally associated with oil and gas drilling. It took about 4 years to reach 7,263 meters. After a long pause, workers replaced it with the purpose-built Ural-Mash 15,000, a highly automated installation designed for a target depth of 15 kilometers. The tower stood over the tundra like an industrial launch structure. But the machinery below it did not operate like a giant household drill. Pressurized drilling fluid powered a turbine near the bottom, turning the cutting head without rotating the entire string. Light alloy pipes reduced weight, while a central receiver captured cylinders of rock for analysis at the surface. At 12 kilometers, lowering or retrieving the drill string could take roughly 21 hours. A single bit might cut only 7 to 10 meters before replacement. Every additional kilometer increased heat, friction, instability, and the consequences of a broken pipe. The engineering achievement was not merely making a narrow hole, it was keeping that hole usable long enough to obtain measurements and core. Core recovery was never complete. More than 70% of the drilled interval was cored, but the average recovery across the borehole was about 40%. At great depth, pressure changes could shatter samples during their long journey upward. Even broken fragments mattered, because their minerals, textures, gases, and fluid inclusions preserved information unavailable from surface observations alone. The original target was 15 kilometers. For perspective, Challenger Deep in the Mariana Trench is about 11 kilometers below sea level. Kola eventually exceeded that vertical distance through rock. But comparisons can mislead. An ocean trench is open water above a seabed, while SG-3 was a branching bore only about 21 centimeters wide near the cutting head. For the first several kilometers, the geological section broadly followed expectations. Then the predictions began to fail. Seismic surveys had indicated a major change in wave velocity several kilometers down. At the time, many geologists interpreted that signal as a boundary between an upper, granite-rich layer and denser basaltic rock below. The Kola team expected to intersect this so-called Conrad boundary around 7.5 to 8.5 kilometers. The drill did not find the predicted basalt layer. The volcanic and sedimentary sequence extended deeper than expected, to about 6.8 kilometers. Beneath it lay ancient gneisses and amphibolites, not the clean compositional boundary imagined from the seismic data. These rocks continued to the bottom of the borehole. The seismic measurements had not lied, and geology was not completely rewritten in a single moment. The interpretation was wrong. Changes in fracturing, pressure, metamorphism, fluids, and rock properties could create strong seismic contrasts without requiring a simple granite to basalt transition. Direct drilling gave researchers a way to test what remote signals actually represented. Below 7 kilometers, the borehole entered Archean rocks more than 2.5 billion years old. They were less uniform and more fractured than the stronger formations above. The walls developed cavities and an elliptical shape. Sections collapsed or widened, making the path increasingly difficult to control. The project did more than pull ancient stone from darkness. It revealed that the deep crust in this region was mechanically and chemically active. Fractures and faults provided pathways for fluids far below depths where many earlier models expected crystalline rock to be nearly sealed. Scientific studies found fluids in fractures and microcracks throughout much of the deep section. Later analyses describe aquifers and highly mineralized waters as deep as roughly 11 kilometers, especially where the borehole crossed major fracture zones. These were not vast underground oceans, and the drill did not suddenly release a river rushing toward the surface. The water's origin was also more complicated than the claim that Earth was manufacturing it directly from hydrogen and oxygen squeezed out of crystals. Deep fluids may have several histories, including water involved in metamorphic reactions, ancient hydrothermal circulation, and components that once descended from the surface. The available evidence does not justify one cinematic explanation for every sample. Gas also moved through the deep system. Reports describe hydrogen, helium, nitrogen, and carbon dioxide in material associated with the borehole. Their presence did not mean a giant pressurized chamber had been opened. Like the mineralized water, they showed that fractures, chemical reactions, and ancient geological processes could transport and preserve volatile substances deep inside continental crust. Even so, the discovery mattered. Fluid-filled fractures affect electrical conductivity, seismic velocity, mineral reactions, and the strength of crustal rocks. At Kola, mineralized water was associated with zones of ore formation at depths previously considered surprising. Later research even identified gold-bearing rocks and ancient fluid inclusions between about 9.5 and 11 kilometers. For the drilling team, fractured, water-bearing rock created practical trouble. Borehole walls could change shape, crumble, or trap equipment. Drilling mud helped cool the bit, carry fragments upward, stabilize pressure, and protect the walls, but it could not make the geology uniform. The deeper SG3 went, the less it resembled a single clean shaft. In fact, the lower borehole became a network. Engineers drilled 12 bypass branches after accidents or obstructions forced them away from abandoned sections. 4 branches extended for more than 2 kilometers. Rather than one perfect line descending from the surface, the deepest part looked more like a narrow underground tree. The bypasses were failures from an engineering perspective, but they created an unexpected scientific advantage. Multiple branches sampled neighboring volumes of the same ancient formations. Researchers could compare changes across a 3-dimensional section instead of relying on one narrow column. Every abandoned route cost time and equipment, yet it also expanded the geological archive returned to the surface. One accident was especially costly. After the hole reached more than 12 kilometers in 1984, roughly 5 kilometers of drill pipe and a turbo drill became stuck and were left below. Drilling resumed months later from a shallower point, creating another branch. It took years to regain the lost depth. Core samples also contained traces of ancient life, but this discovery is often distorted online. Accounts report microfossils in roughly 2-billion-year-old metamorphosed rocks at about 6.7 kilometers, frequently summarized as 24 forms of microscopic plankton. They were fossils carried downward by the geological history of the rocks, not organisms living beside the drill in a sunless abyss. Their presence did not prove that biology survives without oxygen or nutrients at 7 kilometers. It showed that recognizable biological structures could remain in rocks that had been buried and altered over immense spans of time. That distinction matters. Fossil preservation is evidence of ancient environments, not automatic evidence of an active deep biosphere. The finding can still inform the search for ancient life elsewhere. Scientists studying Mars examine whether rocks can preserve chemical or microscopic traces long after surface conditions become hostile. Kola offered an earthly example of old biological evidence, surviving burial and metamorphism. It did not, by itself, open a new program for hunting aliens beneath Jupiter's moons. The most relentless obstacle was temperature. Models had predicted comparatively cool conditions in this stable part of the Baltic Shield. Engineers expected something near 120 degrees Celsius at the planned depths. Measurements later showed about 180 degrees at 10 kilometers, and values reported above 200 degrees near 12 kilometers, depending on the measurement and stage of the project. The rock did not melt into chewing gum. Granite melts at temperatures far above those encountered at Kola, but hot, highly stressed rock can deform more readily, while fractured borehole walls can creep, close, widen, or collapse. Heat also shortened tool life and made downhole electronics, drilling fluids, seals, and materials harder to operate reliably. This distinction makes the engineering no less dramatic. At the bottom, teams worked through 12 kilometers of pipe to control a cutting head they could not see. Inside an unstable path where every trip required many hours, a small failure could abandon years of progress. The planet did not consciously fight back. Ordinary physics was enough. By late 1983, SG3 had passed 12 kilometers. After the 1984 accident and years of bypass drilling, it reached its maximum depth of 12,262 meters around 1990. The desired 15-kilometer mark remained almost 3 kilometers away. Why did they stop? Heat and unstable rock imposed severe technical limits, but the historical record also points directly to funding. As the Soviet system weakened, support fell sharply. Engineers attempted to install casing in 1992 with the hope of continuing toward 13 kilometers. Further drilling was abandoned that year, nor did reaching 12,262 meters establish an absolute physical limit for every future drill. It marked the practical limit of that borehole, with its temperature, rock structure, equipment, budget, and political moment. Stronger tools alone would not solve every problem. Future projects would also need better sensing, cooling, casing, directional control, and sustained funding over many years. At Kola, each problem interacted with the others, turning additional depth into a slower, riskier, and increasingly expensive achievement for the entire team. The site was not immediately deserted, and workers did not simply bolt a cap over the hole before fleeing. Scientific observations continued for a time. Funding ended the remaining research by 1995, and the well was mothballed. The decision to dismantle the Uralmash 15,000 equipment came much later, in 2007. The ruined site and its small metal wellhead belonged to that gradual abandonment. Then the scientific story acquired a supernatural shadow. An urban legend claimed that researchers lowered a heat-resistant microphone into a cavern and recorded millions of human voices screaming in hell. No credible project report documents such an experiment. The tale circulated through sensational and religious media around the end of the Soviet era, gaining new details as it traveled. Audio later attached to it has no verified connection to SG3. The rumor succeeded because the real setting was irresistible. A secretive Soviet installation, a record-breaking descent, unexpected heat, and a sealed opening in Arctic ruins. But the borehole was in the Kola Peninsula of northwestern Russia, not Siberia. It never reached a giant empty chamber, and no instrument returned evidence of the supernatural. Today, an iron disc about 23 centimeters across marks the wellhead amid decaying structures. It does not cover a clean, open tunnel dropping 12 kilometers straight down. Much of the uncased lower borehole has deformed or collapsed, and the branching geometry remains buried in rock. SG3 is still widely described as the deepest vertical borehole ever made. Some modern oil and gas wells have greater measured lengths because they curve horizontally for many kilometers. That does not mean they descend farther beneath the surface. Kola's record concerns true vertical penetration, not total path length. The record has survived partly because repeating the experiment would be enormously expensive. A deeper scientific borehole would require specialized rigs, durable downhole instruments, temperature-resistant electronics, drilling fluid systems, years of labor, and a reason strong enough to justify the cost. It is not simply that modern engineers lack better metal. Scientists have therefore explored another route. Oceanic crust in deep basins is commonly about 6 to 7 kilometers thick, while continental crust can be many times thicker. Research vessels such as Japan's Chikyu were designed with eventual mantle drilling in mind, using the ocean floor as a closer starting point. No scientific borehole has yet drilled continuously through intact crust into the mantle. Experimental companies are also testing non-mechanical methods, including millimeter wave systems intended to heat and break or vaporize rock for deep geothermal wells. These concepts may reduce dependence on conventional bits, but they have not approached Kola's vertical record in field operations. Promising laboratory technology is not the same as a 12-kilometer borehole. The small cap on the Kola Peninsula therefore marks both an achievement and a limit. Beneath it are abandoned branches, lost tools, fractured gneiss, mineralized fluids, and a record of rocks formed billions of years ago. The project did not expose hell, manufacture an underground ocean, or prove that textbooks were worthless. It accomplished something more enduring. By placing instruments and recovering cores where indirect methods alone had guided understanding, SG3 showed how much complexity can hide inside a clean seismic line. Every kilometer replaced a simple model with a more physical Earth, hotter, wetter, older, more fractured, and harder to predict. 12 kilometers sounds immense. Against Earth's radius, it is less than 0.2%. Humanity's deepest vertical journey into its own planet barely scratched the crust. Yet that narrow path was enough to overturn local expectations and reveal that the ground beneath familiar landscapes remains one of the least directly sampled environments on Earth.